Hi there, welcome to Raelene Maths. In this video we will take a look at translating any graph given a parent function or a parent graph or a starting graph. Here we have two circles, a blue one and a red one, both with radius 3. The blue circle has a center at 0, 0, and a point on the circumference can vary, so we will give it coordinates of x, y. I've drawn the circle with a radius of 3, so I can draw a line segment or a radius of 3 here. I can also drop a vertical line down and a horizontal line across to make a right triangle. Now we can see that the height of this triangle is y minus 0, y2 minus y1, and y minus 0 is just y. Similarly, the base of the triangle is x2 minus x1, or x minus 0, which is just x. And then by Pythagoras' theorem, we know a squared plus b squared equal to c squared, and therefore a squared is x squared plus b squared, which is y squared, and c squared, which is the radius squared of 3 squared, or 9. So the blue circle has equation x squared plus y squared equal to 9. The red circle has a center located at 5, negative 8. If we similarly take any point on the circumference, I'll call that point Q, then we can also draw the radius line with a radius of 3. That's the same as the hypotenuse of a right triangle. But now we have slightly different bases and heights, if you will, of this right triangle. This height of delta y is going to be y2 minus y1, so y minus negative 8, which is y plus 8. And this base, or delta x, is going to be x2 minus x1, which is x minus 5. And now, applying Pythagoras' theorem, a squared plus b squared equal to c squared, is delta x squared plus delta y squared equal to the radius squared, which is 3 squared. But delta x is x minus 5 all squared plus delta y, which is y plus 8 all squared, which is equal to 3 squared, or 9. We can actually see this blue equation still says a delta x. It's just that we had x minus 0 squared plus y minus 0 squared equal to 9. And so just to confirm that those are indeed the equations for those circles, let's take a look at a grapher. We have the circle of radius 3, centered at 0, 0 in blue, and the red circle is the same circle translated 5 spaces over and 8 spaces down. So let's now confirm that every point from blue to red goes 5 spaces to the right and 8 spaces down. From center to center, we are going 5 to the right and 8 down. And picking any other points on the circumference of the blue graph to the red, we're going 5 to the right, 8 down, and picking another pair of points, we're going 5 to the right and 8 down. So here we have a vector which is taking us from the blue graph to the red graph, and the components of that vector are positive 5, negative 8. Therefore, if we want to go from the red graph to the blue graph, we have to go 5 to the left and 8 up. And so from red to blue, we have the opposite components of negative 5 and positive 8. And so this negative 5, positive 8 shows up over here in the equation of the circle that we just found. We have x minus 5 and y plus 8. This negative 5 and this positive 8 are the components that take us from red to blue. But if we want to go from blue to red, we have to do the opposite. So when we have an equation like this one down here, x minus 5 all squared plus y plus 8 all squared equal to 9, we do the opposite of those instructions because we are going from the simple blue graph to the transformed red graph. So let's see how this works for a parabola. Very often when we want to sketch a function like y equals x squared, we start by making a table of values. So we work numerically, and in this case let's pick a few x coordinates, not too many. Let's say negative 3, negative 2, negative 1, 0, 1, 2, 3. The easiest number to square is 0. 0 times 0 is 0, which gives us a point 0, 0. Then when x is negative 1 or positive 1, we square, we get 1. If x is negative 2 or positive 2, we square and get 4. and when x is -3 or +3, the square of those numbers gives us y equals 9. So this helps us to come up with the pattern for a basic parent simple quadratic. Start at the turning point or vertex 0, 0, go left or right 1, up 1. Then we go back to the turning point 0, 0, go left or right 2, up 4. Back to the turning point 0, 0, left or right 3, up 9. And so it goes that the distance away from the turning point horizontally gets squared to be the distance that we go up. So here we have our parent parabola, and we are going to translate it once again according to this vector of 5 to the right and 8 down. This is our from the blue to the red graph, and again that vector is 5 to the right and 8 down. And so if we do that, we're not going to resize the parabola. We're going to keep the same size, the same width, the same dimensions. We're just going to drag it over. But let's also recall, since we're not resizing, we have a new vertex. We go left or right 1, up 1. From the vertex or turning point, we go left or right 2, up 4. And then we go left or right 3, up 9. And we can continue on in this pattern, but we should be able to just drag that shape and fit the points because we haven't resized. So we've got that, and we see that because we're going 5 to the right and 8 down, we can come up with a new equation from the y equals x squared. This equation is really y minus 0 equals x minus 0 all squared to indicate a 0, 0 translation for the blue graph to the blue graph. But now if we want to translate to get a new red graph, we have to make use of these translation numbers. But because these are instructions to go from the blue to the red, they will go in as the opposite instructions to take from the red to the blue. The red to the blue instructions will be a -5 and then a +8. And so we put inside with the x a -5, and then inside with the y we put +8. Now this is not how we normally see the equation for a parabola. We normally see y equals x minus 5 all squared and then -8. And we're used to seeing the turning point as do the opposite for x, but not the opposite for y. I would like to challenge that based on what we saw for the circle and also based on consistency and using these components of the vectors from red to blue. Let's confirm that these graphs are actually the graphs of the red and the blue parabolas. So on our grapher we have the circles, and much like the circle I'm going to do the blue parabola y equals x squared, but I'm going to emphasize that this is y minus 0 in brackets, and here before we square it's x minus 0 and then squared. This is just going to emphasize that the center of the circle or the turning point of the parabola is located at 0, 0. And then the center of the red circle is located at +5, -8, and therefore we have the parabola that has been moved over 5 spaces and to the right and 8 down is y plus 8 in brackets equals x minus 5 all squared. And so we can see that we've translated that parabola from blue to red, 5 to the right, 8 down. We are not used to seeing the parabola equation written like this, though. We normally see y equals x minus 5 in brackets squared and then subtract 8. This is fine. It's still the same parabola over here. I'm going to get rid of some of the other graphs now. We don't need them. But what is misleading here, or what is confusing, is when we're told to do the opposite instruction for x, but the direct or same instruction for y. This just seems to be something to memorize without understanding why. So my preference is not to use this form of the equation. And instead we go back to this one because we have consistency. We do the opposite for x, we do the opposite for y, and the reason we're doing the opposite is because these instructions directly go from red to blue, but when we start graphing, we start with the parent or simple graph. so we need to go from blue to red. Now, this isn't completely unseen or unheard of before. We've had other shapes of graphs like lines. Let's take the line y equals 2x as a parent graph. And then let's make a line parallel to this line. So the gradient is still 2, but let's make it pass through the point 5, -8. So to do that, we use a form of the line which I call it the point slope or the gradient point form, and we might know it in a formula way as y minus b equals m times x minus a, where a and b are the coordinates of the point that we want to plug in. Well, we want the line to pass through the point here, 5, -8. So a is equal to 5 and b is equal to -8. But of course, -8 is going to be +8. And so we have the same structure of the y plus 8 in brackets and the x minus 5 in brackets. I want to have the same gradient, so I'll replace m with 2. And so when we do that, we see that our lines are parallel. Let me now turn off the parabolas that are a bit confusing. But we have this structure of y minus b here, which is not what we had in the parabola, which has the -8 on the other side. So for consistency's sake, let's keep the translations in the brackets with the variable it belongs to. Here we are given the graph of y equals f of x, and we're asked to sketch a graph of y equals f of x minus 5 and then subtract 8. This and then subtract 8 really belongs to the y, so I'm going to add 8 to both sides, and now I can see I have a translation vector from the red graph to the blue graph. And that translation vector says to go 5 spaces left and 8 spaces up. But of course I don't have the red graph, I have the blue graph. So my blue to red translation vector is going to be the opposite of those components. It's going to be 5 to the right and 8 down. So I'm going to take every point on the blue graph, 5 spaces to the right and 8 down. Because I'm not scaling or resizing my graph, I can just translate this graph 5 spaces to the right. So if I use my 0, 0 point as my start point, I want that point to map onto 5, -8. And so I'm going to translate 5 right, 8 down, and that's the image that I'm looking for at the end. There's my red graph, which can be written as y plus 8 equals f of x minus 5, or we can go back and isolate y, make it the subject, and call this graph f of x minus 5, and then subtract 8. However, my preference is definitely to use this format because we can see the vector components. Again, the -5 and the +8 here are from the red to the blue. So we do the opposite because we are going from the blue to the red. There you have it. I hope you like this version of translating graphs, slightly different from what we normally see. Thanks for checking out Raelene Maths.